Hi, my name is Dr. Ahmath. From this video lecture, we are going to start learning about the integration techniques. And the first one which we are going to start learning is called the substitution rule. So before we start learning, let's learn about the fundamental theorem of calculus, which basically tells us that if you would like to evaluate the integration of the function from a to the b, just find its antiderivative and just evaluate the antiderivative at the borders of your integration, at the b and at the a, then just subtract them in order to get the value of this integral. Where the antiderivative is essentially the function, so that its derivative is going to give you your given function. So let's do a couple of exercises in order to try to understand what is the antiderivative a little bit better. So let's say you're given the function sine of x, then we easily can find its derivative. So essentially the derivative of the sine of x is going to be equal to the cosine of x. So if you're given another function, for example, the cosine of x, then the derivative of the cosine of x is going to be equal to the minus sine of x. So if you're given, for example, the x in the square, then we can again easily find its derivative. In this case, it's going to be equal to the 2x. So you see, so when I'm asking to find the derivative, you can easily answer to these questions. And what is the integration is about is to find, or is to ask the inverse question. So if you are given the function, what is going to be its antiderivative? F of x, or essentially the function, so that if you take its derivative, you're going to come back to this function again. So if you're given another function minus sine of x, what is its antiderivative? It is cosine of x, because the derivative of the cosine is minus sine of x. You see, so we have to answer to the inverse question. So that if you take the integration of all of these functions, the cosine or minus sine or tx, you're going to get those antiderivatives. So we need to evaluate the antiderivatives at the borders in order to evaluate the integration. So let's do a small exercise. So if we need to evaluate this integration, what we need to do is, for example, from 1 to the 3, we need to find first of all its antiderivative. The antiderivative of the x in the square is going to be equal to the x cubed over 3, and the antiderivative of the 1, it is going to be equal to the x. The reason why the antiderivative of the x in the square is x cubed in the 3 over 3 is because if you take the derivative from the x cubed over 3, you're going to get 1 over 3 times the derivative of the x cubed, which is 3x in the square, which is going to be equal to the x in the square. Okay, so the reason why we chose this to be x cubed over 3, because its derivative is x in the square. And you are given x squared. Okay, and at the same time, the antiderivative of 1 is x, because the derivative of the x is equal to 1. Again, so if you're given 1, so its antiderivative is going to be the x. And we choose this x because the derivative of the x is equal to the 1. And then we have to evaluate this at the borders of your integration at the 1 and 3. And if you substitute the 3, it is going to be equal to the 3 in the square times the 3 divided to the 3 plus the 3 minus, then we have to substitute the 1. It is going to be equal to the 1 over 3 plus the 1. So if you open the brackets, it is going to be equal to 9 times the 3, it's 27 over 3, right? Plus minus 1 over 3 plus the 2, and this is going to be equal to the 26 over 3 plus the 2. So this is how we are going to evaluate the integration. So by finding its antiderivative, then by evaluating the antiderivatives at the borders. So you see, so the integration is a question which is like a little bit more difficult or different from the derivative. So essentially, you need to know the derivatives of many different functions in order to find the antiderivatives all the times. But this is, it appears, not the end of the story, because sometimes you might be given the function where the antiderivative is not so easy to find. For example, you're given the function which is like a super complicated, in this case, it is like a 2x times the x in the square plus 1. Well, in this case, it is not really possible to find the antiderivative right immediately, so we need to use some kind of techniques. And one of the techniques which we are going to use is so-called substitution rule. So we're going to substitute some function with the u, and its derivative also is going to be substituted with the du. So essentially, we are going to use the substitution rule when you can see some function in some form and its derivative inside the integration. For example, I can see here that x squared plus 1 and its derivative, which is 2x, is both inside this integration. So that is why I'm going to use the substitution rule. So essentially, x squared plus 1 is going to be denoted as u. And if you take the derivative from both of the parts, on the left-hand side, it is going to be equal to the 2x times the dx. And this dx is showing you with respect to which variable you took this integration, you took this derivation. So we took the derivative with respect to the x. So that is why I'm just showing this to be dx. And at the same time, derivative of the u with respect to the u is going to be equal to simply 1. And you have to multiply this to the du because you have to show with respect to the which variable you're taking the derivatives. You see, so you found the function and its derivative in both inside this integration, and it helps you to evaluate the integration. So I'm just going to substitute everything connected with the x with the u, so including dx. So it is going to be the integration of, so 2x times the dx, so 2x times the dx, right? So 2x times the dx is going to be substituted with the du. And at the same time, square root of x squared plus 1 is going to be substituted as the square root of u. Okay, so I'm just going to substitute this as a square root of u. And you know, I can integrate this. Okay, so it is going to, its integration is going to be the integration of the u in the power of 1 over 2 with respect to the u. And if you remember, the integration or the antiderivative of the power function is going to be found using the following formula: u in the power of 1 over 2 plus 1 divided to the 1 over 2 plus 1 plus some constant, because this is the indefinite integral where the borders are not defined. Then in this case, on the denominator, you've got the 3 over 2. If it goes to the numerator, it is becoming 2 over 3. And u in the power of 3 over 2 plus the c, and you can substitute the u with your initial function, which is x squared plus 1. It is going to be equal to the 2 over 3, x squared plus 1 in the power of 3 over 2 plus the constant. Again, you see, so you would never guess what is the antiderivative of this whole function without the substitution rule. And the substitution rule is going to be very handy when you have a function and its derivative both participating inside your integration. So let's make a rule. So let's say in general, so if you've got some function, right, so g of x, and its derivative, g prime of x, inside your function, then we can evaluate the integration by making the substitution. Okay, so in this case, we are going to substitute this g of x as the u, and the g prime of x dx is going to be du, so including dx, right? So both of the things, and this is going to be f prime of u, right? So the u is going to be g of x, and its derivative is going to be g prime of x times the dx. It is always important to show the variable of the differentiation. Okay, so this dx or du is showing you with respect to the which variable you've just taken the derivative. So if you took the derivative from the u with respect to the u, then this is going to be equal to the 1, and you have to multiply this to the du. And if you take the derivative of the g with respect to the x, it is going to be equal to the g prime of x, and you multiply this to the dx because you've taken the derivative with respect to the x. And if you just substitute all of these things to here, then this is going to be the f prime of u du. Then usually, if you remember, the f prime of u was simply the f of u. So we usually denote the big F as the antiderivative of the functions, right? Then its integration is going to be found using the antiderivative of this function. So this is essentially is called the substitution rule. Again, if you've got the u, which is differentiable, and if you see the u and its derivative du inside this integration, then just make the substitution. So instead of writing f of g of x times the g prime of x, we're going to make the substitution. We're going to substitute the g with the u, and a whole bunch of the rest of the things, it is going to be denoted as the du, because the derivative of the g prime of x is going to be g of x is going to be g prime of x times the dx. Then if you make the substitution, you're going to get the easier form of the integration. And this method is called the substitution rule. So what we are going to do now is we're going to solve a couple of problems which can be integrated using this method. So let's first of all start with this function. So we need to integrate the cosine of x in the power of 4 plus 2 times the x cubed dx. So now again, I would like to ask you the first question. Do you see some kind of function and its derivative inside your integration? For example, do you see cosine and its derivative minus sine here inside this integration? No, I don't see this, right? But I see that x in the power of 4 plus 2 and its derivative, which is 4x cubed times the dx, is somehow participating inside this integration, right? So let's try to do this. Let's try to use this information. So the x in the power of 4 plus 2 is equal to the u. Again, our goal is to substitute every single appearance of the x with the u. So there should be nothing left with the x. Okay, so you have to substitute everything with the u. If you have decided to make the substitution, then I'm going to take the derivative with respect to the x from the left hand side. This is going to be equal to the 4x cubed, and you have to multiply this to the dx because you've just taken the derivative with respect to the x. And then I'm going to take the derivative with respect to the u from the right hand side part, which is going to be equal to the 1 times the du, right? Okay, so then I'm going to try to make the substitution. So you see here that x cubed times the dx, right? So I have the x cubed times the dx here as well, can be substituted as the du over 4. So I need the x cubed dx, which is equal to the 1 divided to the 4 of du, and I'm just going to substitute this here. So this is going to be equal to the 1 divided to the 4 du, right? And the cosine of x 4 plus 2 is going to be substituted as simply cosine of u, because x in the power of 4 plus 2 was u. And we can really easily find the antiderivative of this function, because the antiderivative of the cosine is sine, because the derivative of the sine is cosine, right? It is going to be equal to the 1 over 4 sine of u plus the constant. Again, the antiderivative of the cosine is sine, because if you take the derivative of the sine, you're going to get the cosine of u. Okay, so this is the reason why we're taking the sine as the antiderivative of the cosine. And then if you want, you can just make the substitution back. So you can substitute the u with the x in the power of 4 plus t. It is going to be 1 over 4, then sine of x in the power of 4 plus 2 plus the c. So you can always check your answers by taking the derivative from your answer. So for example, if you take the derivative from this function, what you get? So the derivative of this function is going to be 1 over 4 times the cosine of x in the power of 4 plus 2, right? And according to the chain rule, you have to multiply this as the derivative of the argument, which is 4x in the power of cube, which is the same function as your initial function inside your integration. This is what you wanted to find. You wanted to find such a function here so that if you take its derivative, you're going to get the given function. So let's do a couple of more exercises. So now in this example, we are going to try to integrate the following function. And again, so the question is, do you see some function and its derivative in some form inside this integration? Well, I can try to do the following substitution. So let's do 1 minus 4x in the square as the u. Okay, then du is going to be equal to, so du, the derivative of the u with respect to the u is going to be du simply. And in the left hand side, I'm going to take the derivative with respect to the x. It is going to be equal to the minus 8x. So do you have minus 8x dx inside your integration? No, but we have x times the dx, right? So if your x times the dx is multiplied to some constant, it is always easy to deal with, right? So you can just put this constant to the right-hand side part, and that's it, because x times the dx is becoming simply minus 1 over 8 du. I think we are ready to make the substitution. So I'm just going to make the substitution of all of the appearances of the x with the u. So here I've got x times the dx, right? Which is going to be substituted with the 1 over 8 du. Multiplied to the minus 1, so which is going to be minus 1 over 8 du. Then on the denominator, you've got the square root of u. Again, I think we are able to do the antiderivative, to do the integration of this. I'm just going to rewrite this little bit in a different form. So minus 1 over 8 u in the power of minus 1 over 2 du. Then I'm just going to use the formula of taking the integration of a power function, right? Which is going to be equal to the minus 1 over 8 times u in the power of minus 1 over 2 plus 1 divided to the minus 1 over 2 plus 1. So on the denominator, you've got 1 over 2. If it goes to the numerator, it becomes simply 2. If it cancels with the minus 1 over 8, it becomes minus 1 over 4. It is going to be minus 1 over 4 times u in the power of 1 over 2 plus the constant. And you can re-substitute the u with the initial function. It is going to be equal to the minus 1 over 4, 1 minus 4x in the square in the power of 1 over 2 plus the constant. So you see, just using the substitution rule, we can find the derivatives or integrations of many, many different functions. So let's do one more exercise. So now let's do this integration. So we have to integrate the tangent of x. You probably remember that the derivative of the tangent is simply 1 divided to the cosine in the square. But the question is, what is going to be the integration of the tangent, right? So the derivative of the tangent of x is equal to 1 divided to the cosine square of x. So that is why if you take the integration from the cosine square of x, you're going to probably get simply the tangent of x. Okay? So now the question is, what is going to be the integration of simply the tangent, not the tangent prime of x. So in this case, we are going to use the substitution rule, but you don't see the function and its derivative inside the integration at this glance. I'm just going to substitute the tangent was the sine of x divided to the cosine of x dx. I think now it is going to be much more clearer that we have to use the substitution rule because we have a function and its derivative inside the integration, right? So I'm going to choose the cosine as the u because dx should come with your function. Okay, so sine of x times is a dx. So I've got sine of x times is a dx. So that is why. So I'm going to choose the u as the cosine of x. Then du is going to be derivative of the cosine, which is minus sine of x dx. So that is why the sine of x dx is going to be equal to minus du. And I'm just going to make the substitution. It is going to be the integration of minus du, because on the numerator I've got sine of x times the dx, right? So divided to the cosine of x, which is u. And if you remember, the antiderivative of the 1 divided to the u is going to be equal to the ln of u, because derivative of the ln of u is 1 over u, plus the constant, or sometimes we denoted this as ln of u in the power of 1 minus 1, plus the constant. So if you want, you can just make the substitution back and write this down as the ln of 1 divided to the cosine of x plus the constant. Well, this is how the substitution rule works. And again, so the main question is you need to be able to know which method, integration method, you need to use in order to find the antiderivatives. So usually finding the antiderivatives or the integration is not the easy job. And you need to always know which method you need to use. And the substitution rule is used when you have a function and its derivative inside your integration. Well, thank you very much for your attention. I hope that this was helpful for you.